So if you're just getting started with Rust and you want to learn a little bit more, get your hands on some code, not get too deep, don't do any huge projects or anything like that, there's this repo called Rustlings that will let you take a bunch of small exercises that have a bunch of tests written for them and get you used to reading and writing Rust code. Now I'm on Mac OS, so I'm going to copy and paste this curl command, which will download a script and pipe it to bash, which runs it. After we run the script, if you see this message at the end, that means everything worked and you don't have to do anything else. Note that this script checks for Git, Rust, Cargo, and some other things. I already have all of these tools installed, so I don't need to do anything else. We can cd into the Rustlings directory. Inside of this directory, you'll see an install.sh and a number of other things. Really, the only directory we care about is exercises. This includes all of the exercises that we'll end up doing. The curl command we ran before installed a CLI tool for us. The CLI tool is called Rustlings. If we run Rustlings watch, we can see an error. This error is in the exercises variables1.rs file. As we work through these exercises, you'll note that we'll first see an error in a particular file. We'll fix the error, and then it'll move on to the next file. In this way, we can use Rustlings watch to go through the entire Rustlings repo. Note that you can also use Rustlings run to run specific exercises, get hints, or verify them. Finally, note that the version of Rustlings that we are going to use includes a couple exercises that aren't necessarily included in watch, or aren't necessarily ready for people to do, or aren't documented enough. Those are listed here. Let's get started. I've opened the Rustlings directory in a VS Code window. Note on the left, I've also opened the exercises directory, as that's the one we'll be focusing on the most. And on the right, I have a terminal window. After running Rustlings watch, we see that when compiling exercises variables1.rs, it failed. Before we get into the error, let's open the file. On Mac OS, if I type Command P, it opens this bar at the top of the window. I'll type variable to get a list of the files with the variables in their name, and choose variables1.rs, which is the file in the error. I'm going to close the sidebar, but you can also look at the output here and follow that path, variables1. There's a couple comments here. In variables1.rs, which is a Rust file, we see a single function named main, the body variable declaration x equals 5, and a print line macro that prints x has the value and formats the value of x into this place in the string. If we look at the error, on line 12, we have x equals 5. If we read the error, we say cannot find value x in this scope, which is strange because it looks like it's defined on the left. Note that we have the same error in both places. In Rust, we need to define variables with the word let. If we type let x equals 5 and we save, we can see that Rustlings watch ran the tests that we needed for the files that we changed. And now x has the output 5. Now that we've done our first exercise, we can keep playing with this code. Say change the user. Say if we wanted to change this into a string or a number, or we can remove this comment to move on to the next exercise. Once we remove the comment, the next exercise pops up in variables2. In variables2, we have a function named main with a function body that declares an x variable with an if statement. If x is 10, we use the print line macro to print 10. Otherwise, we print not 10 using the line macro. Looking at our error, Rust has said we need type annotations, so we can consider giving x a type. Rust has both unsigned integers and signed integers. Since x is only going to be 10, it doesn't matter which one we use. Note that we've added the signature by using a colon with the type after it. This gives us a second error, use of possibly uninitialized variable x. This is because x hasn't been initialized. We've declared the type of it, but we haven't given it a value. If we set x equal to 10, with the type declaration on the left-hand side of the equal sign, we can see that our test passed. We can see this is also true if we set x to 11. And now onto variables3. For variables3, we have our main function again, with an x that equals 3, a print line macro that prints the number, a reassignment of x to 5, and another print line macro that prints the number again. Here in our error, we can see that we cannot assign twice to an immutable value. The error points to x and says the first assignment to x, help, make this binding mutable, mute x, and then follows up with the error that we saw above, cannot assign twice to a mutable value. So we're doing an assignment here and an assignment here. And because Rust is immutable by default, we can't assign twice to a single value because that would mutate the value. As seen in the error message, we can use the mute keyword to set the x variable to a mutable value. This lets us assign to x a second time. In variables 4, we have a main function yet again, with an x that is typed as an i32, which is an integer, and a printline macro that prints number and the value of x after the number. Our error message says we have a borrow of a possibly uninitialized variable, and it points to x as being the possibly uninitialized variable. In this case, if we initialize the variable to any value, preferably an i32 value, the program compiles and runs. In variables 5, we have a main function. The body of the main function sets a number equal to the string 3, a printline macro that prints out the number. We reset the number to 3, an integer, and then we use a printline macro to print the number again. In this case, Rust has told us we have mismatched types. When we set number to 3, the integer, Rust expects a reference to a string, and it finds the integer. Now we know that we can put a mutable keyword here to let us set the number to a different value. That doesn't really help us though, because we still have the same error. Let's take a hint Rustlings. Now I'll let you read this on your own, but basically it says exactly as said, where in variables 3, we used the mute keyword. But that doesn't help us here, because we're converting between two different types. The change that we need, as the hint has given us, is shadowing. This lets us take one variable that's in scope and create a new scope inside of which we can redeclare that name and use it with a different value. The number name inside of this block lives for the length of this block, while this number lives for the length of the entire program. After variables 5, Rust takes us into the land of if statements. If we look at our program, we have a set of tests. We'll mostly ignore tests for now, except to mention that they are written in the same file, and that if you have a VS Code plugin, you can actually run the individual test on its own. Note that in our file, we have a function called bigger that takes an A and a B, both of type i32, and it returns a value of i32. This means that A and B are both integers, 32-bit integers. This means that both the arguments A and B to our bigger function are 32-bit integers. The instructions in the comments tell us to complete this function to return the bigger number. We cannot use another function call, which in this case, I'll let you know that there is a max call in the Rust library. And we also can't use additional variables. So we'll say if A is greater than B, return A, else return B. Know that this works. Also note that we've used implicit return values because this is the last statement in our function, and thus these are the last values encountered. We can also be explicit about this and write the return statements explicitly. In functions 1, we have a function called main that calls a function callMe with no arguments. In our error message, you can see that it says cannot find function callMe in this scope. That's because we don't have a function named callMe anywhere. This file is everything that Rust is looking at. Note that if we copy exactly what we have for main and rename it to callMe with no return value, our tests pass. This is how we declare a function in Rust. In functions 2, we have a function that uses callMe and passes the number 3 to it. Functions 2 defines callMe for us and says it takes an argument of num. The code here uses a for loop for I in, and this is called a range. This will create a sequence from 0 to whatever number we have. For example, if it was 5, 0, 1, 2, 3, and 4. This for loop will loop over that range and use the printline macro to print call number and then format the number plus 1 into this location in the string. If we look at our error, we can see that the Rust compiler is looking for some tokens, either a colon, an at, a pipe, or an ending parenthesis. We also see a note about anonymous parameters. If you're interested, you can look more into that, but it's not important, especially if you're learning Rust with the 2018 version, like you probably are right now. We can see a number of suggestions in the help, such as if this is a self type, which we might cover later, give it a parameter name. If it was a parameter name, give it a type. If this is a type, explicitly ignore the parameter name by using an underscore. In our case, the one we want is this one. Num for us is a parameter name, but it doesn't have a type. We'll use a colon like we did when we did variables for this to be a U32, an unsigned 32-bit integer. And we see that our range goes from 0 to 2, which results in the numbers 1, 2, and 3, because we add 1 to each in the range. In functions 3, we start with the code that we ended with in functions 2. The only difference is that callMe has not passed any arguments, but we've defined me as taking a number. To fix this, we can pass any number into the function call. Note that we now have all 10 numbers in our output, and our tests pass. In functions 4, let's reverse what we've been doing and take a look at the error message first. Expected type found brace. At line 14, function sale price. Price is an I32, and there's an arrow here where Rust expected a type. If we find line 14, we can see that sale price takes a parameter that is an I32 and doesn't have a return value, even though we've used the arrow here. If we remember back to our if statement, we can see that we're implicitly returning price minus 10 or price minus 3. In that case, we can probably use an I32 since that's what the parameter is, and we're operating with integers on it. And note that our tests have passed. In functions 5, we have our main function with an answer set to this value of square 3, and we use another printline macro to print out our answer. The square function takes a number parameter that's an I32 and returns an I32. All we're doing here is squaring the number. The Rust error tells us there's mismatched types, specifically in the square function that we just took a look at, and it points to the return value of I32, where it expected an I32 and found two parentheses. These two parentheses are usually pronounced unit, U-N-I-T. A unit type is basically nothing. So what Rust is telling us here is that this function implicitly returns nothing as its body has no tail or return expression. We have a little bit of help text here that says, consider removing this semicolon. So let's try that. And note that this works because the implicit return requires you to not use a semicolon at the end. If we were going to use a semicolon, we could also use an explicit return, and that would work. Now we meet our first real test. Up until this point, we've been going through exercises. This test file is a test for variables and functions as we've done the exercises already. In this case, all we have is a test. We can see the function verify test that is marked with a test. We can see price1 is equal to calculate apple price 35 and price2 is calculate apple price 65. Then we have an assert equal macro that checks to see that 70 and price1 are the same and 65 and price2 are the same. Our Rust error message tells us that the calculate apple price is not found in this scope, which is true because we haven't put our function in yet. So we've included a function signature, and we got quite a bit of output. For example, this function takes 0 arguments, but 1 argument was supplied. That is, the calculate apple price in the test is supplying an integer for us, but our function doesn't take one yet. If we fix that and use a type for it, we see that we get a new Rust error, can't compare integer with unit. Specifically, it's pointing to the assert equal macro and saying that we can't compare 70 and unit. If we look back at our function, we can see that we aren't returning anything in the type signature, which is why Rust is giving us this error. After fixing the type signature, we still have a mismatched types error. Rust expected an I32 and found unit, because we're implicitly returning unit because the body doesn't have any tail, which is a final expression, or an explicit return. This is when we have to go back and read what the actual function is supposed to do. It says Mary is buying apples. 1 apple usually costs 2 rust bucks. If you buy more than 40 at once, each apple only costs 1. Write a function that calculates the price of an order of apples given the order amount. No hints this time. So just from looking at the tests and following the Rust error messages, we've gotten to a point where we have a function that takes a number and returns a number. Inside of the body of our function, we need to see if we're buying more than 40 apples. If we are buying more than 40, the apple price is going to be the same as the number of apples that we passed in because they cost 1. Otherwise, they cost 2. And finally, we can see that this implementation and the type signatures satisfy everything that Rust is looking for. In primitive types 1, we're supposed to fill in the rest of the line that has code missing. No hints, no trick, just get used to typing it. If we look at the error message, it says expected identifier found keyword if. That's because we have a let statement here that doesn't finish anything. That's because we have a let statement here and the code isn't finished on this line. So it goes to look for if to see the next piece of the code, and it's not expecting it. So above we have let is morning equals true. If is morning, then we use the print line macro to print good morning. Here we're checking is evening, so we'll also set that to true, and our tests pass. Here we're using a Boolean value of true and setting it equal to is evening. In primitive types 2, we have a main function with a body that sets my first initial to the character C. We know this is a character because we used single quotes here. Double quotes indicates a string. We have a number of functions that are called on a character that don't exist on strings. And on line 19, we have to finish the line. Note that the error message doesn't do us much good here because we need to finish the let line, which is missing code. In this case, we'll take your character, which is the variable that we need, and try to set it to a string. You'll note that because we used double quotes, there's no method named isAlphabetic found for reference and string in the current scope. If we change this to use single quotes, and remember to add our semicolon, then our tests pass. IsAlphabetic and isNumeric are functions on characters, not strings. In primitive types 3, we can see that the Rust compiler expected an expression at ? On line 8. We're supposed to create an array with at least 100 elements in it. Now, we could type out an array with 100 elements in it, but that would be quite time consuming. Instead, we're going to use a range. 0.100 creates an array with the values 0 through 100 incrementing by one integer. So 0, 1, 2, 3, 4, 5, 6, etc. Thus, we have an array with greater than or equal to 100 numbers in it. In primitive types 4, we're supposed to get a slice out of an array where the question marks are, so the test passes. Note that we have a 5-element array, 1, 2, 3, 4, 5, and we're using the assert equal macro to test that 2, 3, 4 is equal to our nice slice. That means we need to get elements 2, 3, and 4, which are 1, 2, and 3 index. To do this, we can use a special syntax. We can use a range here, like it's a property on A. The range will start at the starting index and end at the ending index. We're starting at index 1, which is 2, and we're ending at 4, which will not include the 4th index. Note that we get an error here. The size of the slice can't be known at compilation time. Consider borrowing here. After including the borrow symbol, the ampersand means we're using a reference to A. So in effect, we're borrowing a section of the array as a slice by using a range. Primitive types 5 introduces us to the cat tuple. We declare a variable cat that is a tuple, that is, it starts with a paren, ends with a paren, and the values are separated by commas, where the first value in the tuple is a string and the second one is 3.5. We have to include a pattern here to destructure these values such that we can use them in our printline macro call. Note that we can destructure a tuple on the left-hand side of the assignment by giving a name to each position in the tuple. In primitive type 6, they want us to use a tuple index to access the second element of numbers, which is a 3-element tuple. We can do it right where the question marks are. Note that this test is actually buggy and that any index we use here will work, but that tuples are also 0 indexed. So the second number is the first index, 0, 1, 2. We have quite a bit of code in structs 1, including an empty struct here that we need to put something into, a tuple struct here that we also need to put something into, and a unit struct that derives debug. On line 15, our tests start. In each of these tests, we're going to instantiate one of our structs, whether it's a classic struct, a tuple struct, or the unit struct that derives debug above. The errors that Rust gives us don't really help us here, because we already have these to-do comments to tell us what to do. In this case, we've got green.name and green.hex for our first struct in our first test. This struct refers to our color classic struct, so we'll take a first swing at this by naming them strings. Note that we also need to instantiate a new struct. And note that the errors that the Rust compiler is looking at have moved down to line 37, which indicates that our test was passing and that there weren't any problems with it. What we've done here is created a struct with 2 fields on it that are name and hex. These values are strings, which means that the struct is going to own these. To create a string, we use string from and pass in a string literal. Note that if we don't use string from, Rust will tell us we're using mismatched types on lines 24 and 25. We could also use a type and string here, but we're going to stick with strings and use string from. Next, we have to do our tuple struct. Our tuple struct is currently empty, but it uses the same values. You can see that we access the tuple via tuple indexes, like we did in some of the primitive exercises. We're going to end up using the same types that we did in our classic struct, but note that they aren't named. So while we have name and hex in our classic struct, our tuple struct is dependent on the position. If we go back down to our test, we can instantiate our struct. Now that we've instantiated our classic struct and our tuple struct, and our tests are passing, we can move on to the unit struct. The unit struct was created for us, and there's nothing else we need to do. Note that this is called a unit struct because it doesn't have any fields, like the tuple struct has some, and the classic one also has some. Since our unit struct doesn't have any fields, we can set unit struct equal to unit struct, and it works. If we try to take the same approach that we did with the unit struct with our classic struct, which does have fields, you'll note that Rust gives us an error. You'll note that the Rust compiler informs us that color classic struct does in fact have fields and that we need to include them here. Structs 2 is a similar setup in that it asks us to address all the to-dos to make the test pass. So let's take a look at the code that we have. We have an order struct that has a number of fields of different values, booleans, unsigned 32-bit integers, strings. We derive debug. We have a create order template function that looks like it's called on line 36 as well, that returns one of these orders with a set of default values. In our test, we can see that we have an order template that's created with these default values, a number of assertions, and a to-do statement that tells us to create our own order using the update syntax and template above. So we have order template already, and we're going to take order, and all we're going to do is use this like object rest spread type syntax that uses 2 dots with the name of the template. And what this does is what's called update syntax. Order is a struct, and any of the fields that we haven't specified values for are filled in by order template, which is these default values. Now that we have our fill in, we can take a look at the tests that are passing and say panicked at assertion failed, left equals right, left Bob, right hacker in Rust. So we're asserting that your order.name is equal to hacker in Rust, whereas the order template gives us Bob. So let's specify our name to be hacker in Rust. And we've passed that test. So see what's happening here is that we're instantiating a new order. We're specifying that the name of this new order is hacker in Rust, and any of the fields that we haven't specified are these default values. Let's finish up. Note that all of the rest of the assertions, except for the count, are the same as the default value. Also note that if you're used to object rest spread syntax from other languages, that's not the way this works. We cannot put this order template update syntax at the beginning of our record. It has to be at the end. Strings 1 tells us to make it compile without changing the function signature. This is because the Rust error that we're getting expects a struct of string and found a reference to a string instead. The compiler gives us a helpful message that says we can use toString to go from a reference to a string. Note that we're using an implicit return here, so this works. We can also use the from function from the string module, which will also work for this use case. In strings 2, we once again have to make it compile without changing the function signature, specifically line 8. In our main function body, we let word equals string. Then we have an if statement that calls a function defined on line 16. Is a color word takes a word and uses the printline macro to print out that is a color word I know, or that is not a color word I know, depending on the value. Is a color word takes a reference to a string as the attempt and returns a boolean. We use an implicit return to do a number of checks and fall back to the last value. The error message that the Rust compiler is giving us tells us that on line 9, the parameter expected a reference to a string and found a struct string instead. It's also telling us that we could consider borrowing here. If we follow the Rust compiler's instructions, and we use a reference to the word as an argument to is a color word, which is what the type signature is asking for, the tests all pass. Test 2 is a test for the strings section that we went through previously. In this file, there are 2 functions. One is a string slice function, and one is a string function. The only difference between these 2 functions is that they take a different type argument. String takes the string struct, and string slice takes what's called a string slice, that is, a reference to a specific point in memory. In our main function, we have a bunch of parentheses where we need to introduce one of these functions to the beginning of each of these calls, depending on whether we think the value is a string slice and thus accepts a string slice as an argument, or accepts a string. In the first case, we have a string literal, so I'll use a string slice for that. Note that the Rust errors are not going to be super helpful until we have working code here. On line 21, we have a string slice that we run toString on. On the right, we have the string documentation in the Rust docs. I happen to know that toString is an implementation of the toString trait on the string struct. If we go down to the implementation and we expand it, we can see that the function toString on string returns us a string struct, in which case we can put string on the start of this function call. The string module includes a function called from, which is an implementation of the from trait. The from trait is used to do value-to-value conversions and consumes the input value. It has a relationship with into, which we'll talk about in a second. So this will also be a string. The next example we have is a string slice with 2 owned called on it. ToOwned is an implementation of the ToOwned trait, which is a generalization of clone. What this means is that we have the string slice, and that ToOwned under the hood will do a clone of this value. So this will also be a string because we'll gain ownership of it. Niceweather.into is a string slice that we call into_on. This is similar to what we did before with from the other side. So with from, we're saying that we're going to create a string from this value. And with into, we're going to take the value and say that we're going to put it into something, in this case, a string. Note that when using into, because we're taking the value and we're putting it into another value, as opposed to saying we're creating a string from a value. If we use string slice as opposed to string, into will put this value into a string slice instead of a string. The format macro can be found on the macro standard format docs page. The only indication of what this macro returns is contained in the first paragraph. It creates a string using interpolation of runtime expressions. So this will also be a string. On line 26, we have a reference to a string, as we've seen on line 22, that takes a slice. So this will be a string slice. On line 27, we have a string with some extra white space that we call trim on. If we go to the string struct docs and we look for trim, we can see that there's a public function trim on string that returns a string slice. On line 28, we have a string slice that we call toString on, which gives us a string that we call replace on. If we look at the replace definition for the function on string, we can see that it returns a string. So this will also be string. And finally, we have to do toLowercase. If we look for toLowercase, we can see that it also returns a string. If we save, we can see that we have correctly defined all of these. In enums 1, we have an empty enum here. An enum in Rust is a type that can be any one of several variants that we define inside of the body of this enum. In this case, our main function provides us with the ones that we have to implement. These are quit, echo, move, and change color. Because none of the variants in the message enum take any values, we can declare them in the body of the enum. In enums 2, we have an empty enum called message. We also have an implementation of message that defines a function call. This call function we use in our main body. The call function takes an argument of self, which is what allows us to call message.call. The list of messages that we're operating on include message.move, message echo, message change color, and message quit. In addition to the enums that we've defined before, a variant inside of an enum can be any struct. You can see that in the Rust errors, we can see no variant named move for enum message, no variant or associated item echo for each of the variants that we're using. So we first need to define a variant move that has an x, which will make an unsigned 32-bit integer, and a y, which is also an unsigned 32-bit integer. These are arbitrary choices. You can choose really any integer type here. Echo, on the other hand, takes a string. Change color takes 3 integers, which from context we can infer to be the RGB channels in, say, an RGB declaration. In this case, we'll use 8-bit integers. And finally, we also have to define quit, which takes no arguments. And as you can see in this enum, each of the variants can be defined to take additional arguments, whether those are struct-like or single values. In enums 3, we have to address all the to-dos to make the test pass. We have one to-do inside of our empty message enum that we have to fill in. We have to go discover all the message variant types that this enum will need to support. Note that we have a point struct here, a state struct, and an implementation of the state struct that attaches a number of methods. These include change color, quit, echo, move position, and process. Process is an empty body that we have to fill in. In our tests, we have a function called test_match_message_call, where we instantiate a new state struct, and then we have state process each of our messages that come from the enums. Note that some of the errors that the Rust compiler gives us are that we have no variant name moved for enum message, and other such missing variants. We'll do those first. We need change color, echo, move, and quit. Note that I've chosen types for the enums that match the color state, the change color function, or the point struct. All of our numbers are unsigned 8-bit integers, so that's what I used. Also note that echo takes a string, so I've added that as well. Now that our struct is filled out, we can see that some of our tests are not passing. The first one that isn't passing is related to the change color function. When we process this change color, we aren't applying the values. Inside of process, it tells us to create a match expression. We'll match on message, and we'll match on change color. For change color, state has another function called change color, whose first argument is a mutable self, and second argument is a color tuple. To access this function, we'll use self, which is also an argument to process. Note that I've called self.changeColor with RGB as a tuple. We do have one more problem. ChangeColor isn't found in this scope, even though we've defined it up top. This is because ChangeColor is inside of the message enum, so we must use this very specific syntax to access it. Now that we've implemented ChangeColor in our match expression, we can see that we have a non-exhaustive pattern match. We're matching on ChangeColor, but we aren't matching on any of the other variants, such as echo, move, and quit. We'll add those in now. Note that we also have to namespace echo, move, and quit. After pattern matching on echo, move, and quit, we've bootstrapped them with empty blocks that don't do anything. This is fine because process doesn't return anything, so we can use this as a placeholder while we figure out what's wrong with our tests. Our next assertion says left 0, right 10, which is the assert equal on state.position.x, and is related to the move variant in the message enum. If we look at state, we can see that there's a move position function that we should use. The move position function takes a point. When instantiating a new point, we can pass in the x and y. The next test that's failing is for state.quit. We'll call self.quit when we match on message quit, and note that all of the tests have passed. There is one more function we can implement. Because the types match, when we run state.process message echo with a string, currently our empty block satisfies that constraint. But we also have an echo function on our state implementation, so let's implement that. After calling echo, we've implemented all of the variants in our message using a match. We've pattern matched on each of the variants and their values, and then called methods that are on the implementation for state with their values. In tests 1, we encounter our first assert macro. In this case, we have a module tests with one test. The test is that we can assert. So using the assert macro to test whether our value is true or not, we can pass in a true value. Any Boolean expression here will work with the assert macro. When writing tests, we have access to a number of macros. In tests 1, we learned about the assert macro. In test 2, we learned about the assert equals macro. Assert equals will compare two values for us. Note that these values don't need to be Boolean values, but they can be numbers, strings, or anything else that can be compared to each other. In test 3, we have a public function, isEven, that takes a number that's a signed 32-bit integer and returns a Boolean. We're checking to see if the number is divisible by 2. At first, we have to assert that isEven successfully passes through an even value. We'll create our test named isFalse when odd by creating another function. We'll use the assert macro just like our first test did, and we'll pass isEven 5. Note that this passes, and we've successfully written a new test. Note that even though it looks like our test is run, it actually hasn't. If we test isFalse when odd, and we assert isEven 4, we can see that it didn't work. This is because we haven't specified yet that this is a test. Note that now when we pass 5 to isEven, our test is failing, whereas before it wasn't, because it wasn't running. In this case, we can use the assert equal macro with a value of false, and the result of isEven with the argument 5. If we change it to 4, we can see that our test is still running and fails. Exercises test 3 is a test for the tests section that we just went through. Currently, the comment in this file tells us that the test isn't testing our function. Make it do so in such a way that the test passes. Then we have to write a second test that tests what happens when we call our function times 2 with a negative number. Again, we have our public function times 2 that takes a number and returns a number. The body of the function implicitly returns number times 2, and then we configure our test module. In this case, returns twice of positive numbers, uses the assert equal macro to test times 2 on 4, which is 8. Now we have to do the same thing for negative 4, which will be negative 8. We can test to make sure that our test is running by making it fail. In modules 1, we have a module called sausage factory, inside of which we define a function called makeSausage that uses the printline macro to print sausage to the console. Inside of the main function, we call the sausage factory module makeSausage function. The Rust compiler has a problem with this because makeSausage is private, so we can't call it from outside of our module. To change this, we can specify our function as a public function, and now it's available in scope. In modules 2, we have a delicious snacks module that uses self-fruits pear as fruit and self-veggies cucumber as veggie. We can see that inside of this module, we have an additional module called fruits, and an additional module called veggies, which is what these use statements refer to. Inside of our fruit and veggie modules, we have public constants, pear, apple, cucumber, and carrot. These constants are string slices with static lifetimes. In our main function, we use the printline macro to print our favorite snacks, which are delicious snacks fruit and delicious snacks veggie. The Rust compiler tells us that the constant import fruit is private inside of the delicious snacks module. One way we can solve this is by making our use statements public inside of the delicious snacks module. This exposes each of the individual constants, but not the other ones involved in the fruits and veggies modules. So now, in the end, we have our delicious snacks module that exports a different interface than the internal fruits and veggies modules. In macros 1, we learned how to define our first macro. In this case, we use the macro rules macro to define a macro with the name myMacro that returns a function that uses the printline macro to print check out my macro. The Rust compiler tells us that we cannot find function myMacro in scope. This is because we're not calling a function here, we're calling a macro, and macros are called with an exclamation point. Macros 2 has a very similar setup to macros 1, where we have a main function with a body that calls our macro, and a macro rules definition that defines myMacro with a print line. The help message from the Rust compiler asks us if we've added the macro used on the module import, and it warns us because we have the unused macros warning turned on, which is on by default. However, macros need to be defined before they're used, so if we switch the order of the main function body and the macro, our tests work. This ordering for macros needing to be defined before they're used is different than most other things in Rust. In macros 3, we have another scoping issue where we have to make this compile without moving the macro out of the module. Note that we use the macro in the main function, while the macro is defined in the macros module. As we've seen before, you might think that putting pub in front of macro rules would fix this problem, but it does not. However, using pub in front of macro rules points us to the actual solution. The Rust compiler suggests using the macro export. If we follow what the Rust compiler tells us and put macro export on top of our macro rules, our macro is now available in scope. In macros 4, we define a macro using the macro rules macro that has two implementations. One is a function that doesn't take any arguments, and one is a function that takes an expression. In both cases, we use the printline macro to print out the value. In our main function, we have myMacro called with no arguments, followed by myMacro called with 7777. The Rust compiler tells us that no rules expected the token left parenthesis. In this case, all I'm going to do is insert a space and save. Note that our tests are now passing. This is because the semicolons were inserted for me by rustfmt. Rustfmt is a tool for formatting Rust code similar to Prettier in the JavaScript ecosystem, or GoFormat. It's an incredibly useful tool, as we just saw in this module, and you can set it up to be run in your editor. Test 4 covers modules and macros. We have to write a macro that passes the test. In this case, we have test myMacro world with an assert equal macro that calls myMacro with an argument of world and the value of hello world. Similarly, we have another test on line 21 that tests myMacro with an argument of goodbye and says hello goodbye. We can use the macro rules macro with the name myMacro to define our macro. In this case, we're saying that we take an argument and we'll want to use the format macro. We use the format macro with the word hello, followed by a replacement, where the replacement will be the value that is passed in as an argument. Note that our tests are now passing. So we've written a macro with macro rules called myMacro that takes a value as an argument and returns the value of format with hello and a default formatted value in that string. In move semantics 1, we have two vectors. We have a vec0 that is a new vector, and we have vec1 which calls fillvec on vec0. Fillvec takes a vector of i32s and returns a vector of i32s. Inside of fillvec, we create a new mutable vector that's equal to the argument vector, and then we push 3 values in and return the vector. In our main function, we use the printline macro to print out vec1, the length of vec1, and the content of vec1. We then push 88 into vec1, and we do the same again. The problem with this code is that we cannot borrow vec1 as mutable, as it was not declared as mutable. So in this case, the problem is at vec1.push88, where vec1 is immutable by default, which means that we can't use the push function on it. If we add mut to the beginning of vec1, like the Rust compiler says that we should, then our code compiles. We've now created vec1 as a mutable vector such that we can push into it. Move semantics 2 has the same structure as move semantics 1, where we have a vec0, which is a new vec, and a mutable vec1 that we fill with a number of values. We then print out some information using the printline macro, push 88 in, and print again. Note that this time we have a borrow of moved value vec0, and this is because vec does not implement the copy trait, so it cannot be automatically copied, which means that we have to move the value into the fillvec function. When we call vec0.length, on line 13, we've already moved vec0 into the fillVec function, so we no longer have access to it. So when we try to borrow it to get the length, we can't. We can fix this in a number of ways. For example, if we clone vec0 as the argument to fillVec, then we're not moving vec0 and such can access it later. Instead of cloning, we could also make this a reference, which means that the value that we pass into fillVec would also need to be a reference. In move semantics 3, we're supposed to make a compile without adding any new lines and just changing existing ones. In this case, we can't borrow vec as mutable inside of fillVec on line 20. In contrast to the last two move semantics, we aren't creating a new vec inside of the fillVec function this time. If we specify that we want to mutate vec in our type signature, we can then mutate vec in our test pass. Move semantics 4 is set up in a very similar way to the last three move semantics exercises. The difference is that fillVec doesn't take anything as an argument. On line 23, the Rust compiler tells us that it expected a value and found macro vec. That's because to initialize a new vector, we can use the vec macro. Note that there are a number of values we can use here, but we're going to use an empty vector to start. And also note that the Rust compiler expected us to do something after the vec macro. Finally, we're still passing in vec0 on line 12 to the fillVec function. FillVec doesn't take any arguments, so we'll remove vec0. Note that vec new can no longer infer the type that the values inside of the vector can have, but this is fine because we aren't actually using vec0 anymore, so we'll just delete that entire line. And now our code compiles. We have a mutable vector that we fill via a separate function that takes no arguments and returns us a new vector created with the vec macro that we can then push 88 into later. In errors 1, we have a public function named generate_nameTagText that takes a string and returns an optional type. An option type allows us to return either a string or none using the some or none keywords. This is great for signifying errors, as we can return none if we can't get the value, or some value if we can, but it doesn't let us communicate the reason something failed. For that, we're going to use the result type. In generate_nameTagText, we've changed option to result. Option in other languages is sometimes called the maybe type or optional type, whereas result is sometimes called either. In this case, we have two constructors that we can use, which are OK and error. We'll replace some with OK, and we'll replace none with error. In our test, we can see the exact string that we want to pass in as error. Note that if we try to write a string literal, the Rust compiler tells us that we expected the struct string and found a string slice instead. We can use string.from to fix this. Note that in our first test, we're still expecting some as the result of generate_nameTagText, and we should be expecting OK. And now, when our function gets called, we can verify that in the case of a valid value, we get OK wrapping the value. And in the case of an error, we get error wrapping the error value. This allows us to pattern match on OK or error whenever we execute generate_nameTagText. In errors 2, we have a function called total cost that we use in some tests. Total cost takes an item quantity as a string slice and returns a result as either an i32 or a parse_in error. Note that because item quantity is parsed into an i32 so that we can do some math on it, the item quantity can be anything, including invalid numeric values. This is causing us two problems. One is that this value, when parsed, could be an error or could be fine. And the second is that quantity, as the Rust compiler is telling us, is a result value that cannot be multiplied with other integers. So we have to find a way to unwrap this result value to be able to use it in the OK, and we also have to handle this error. There's a small way to do this in Rust using a question mark. The question mark takes the result of parse, and if it's OK, because parse returns a result, quantity will be the unwrapped value, that is, the raw number that got parsed out. Whereas if parse fails and returns an error, the question mark doesn't early return for us, and our function will return the parseInt error at this location. This allows the Rust compiler to know that quantity is going to be a number and that we don't have to operate on the result type anymore. In errors 3, we have a main function that includes the usage of the question mark that we used in errors 2. Note that we also have a usage of the question mark in our total cost function. The Rust compiler tells us that the question mark operator can only be used in a function that returns result or option, or another type that implements the try trait. Luckily, in Rust 2018, we can specify that our main function returns a result type. Now the error is going to be a parseInt error, because that's what total cost can return, which means that this question mark will return the parseInt error from total cost, and this question mark will return the parseInt error that we returned from total cost, but return it to main. So we know that the error that main can return is a parseInt error. We still need a value here, and you'll note that we don't return anything else from the main function if we succeed, so this value will be unit. Note that if you use a fat arrow, instead of a skinny arrow, the Rust compiler will tell you that it expected a semicolon or a brace. And similarly, in the result type, that is the return type for the main function, if you use parentheses instead of the greater than and less than signs, you'll get a Rust compiler error about only function traits may use parentheses. Use angle brackets instead. Finally, once we've declared that main can return a result type, we need to make sure that our main function actually returns a result type. We can do this by implicitly returning OK with the unit value at the end of our function. In errors n, we have quite a bit of code, almost 115 lines of it. We have a number of use statements, a read and validate function, which is the one that we care about, a test with string function, and a number of tests. Note that the problem right now is that we need to specify a type in the result for the error type, but that our function can return multiple different kinds of errors, including one from parse here, up to 2 different kinds of errors from positive non-zero integer, new, and one from readline. We can use the question mark operator to return the errors when they happen, but we still need a type here. Because there are multiple different error types, we used a boxed dynamic error for the result error. This is a runtime way of determining which error is being returned from this read and validate function. Note that because we're returning a result type, we'll also have to return OK answer, and our tests pass. If we know explicitly what errors we can return here, with more boilerplate, we can specify them so that they're statically analyzable for the rest of our program. But in this case, the dynamic error works fine. In option 1, we have a print number function that takes maybe number, which is an option U16. The printline macro unwraps the maybe number and prints the value. We use print number on 2 numbers, and then we also have a separate unrelated piece of code that is a mutable numbers array that contains the option U16 type 5 times. In this case, we haven't yet initialized numbers, and we iterate over the range 0 to 5 and let number to add, which is a U16, equal some math. Then we set the value at the index that the iteration specifies in numbers to the number to add value. The first issue that the Rust compiler tells us about is that it expected an enum option and found integer when we're trying to call print number 13. This is because the function takes an option value, which we can instantiate with sum. While this fixes most of our problems up top, on line 19, indexes into arrays cannot be of type U16. We'll treat this as a usize. Also note that on line 19, the number to add needs to be an option value, so we'll instantiate that with sum as well. Finally, we have a warning and another error. The Rust compiler tells us that we're using a possibly uninitialized numbers array on line 19. This is true, and we can instantiate this numbers array with a set of default values, using similar syntax that we used to specify the size of the array in the type signature. We now have a numbers array that is mutable and contains none values for all 5 values. In option 2, we have a main function that takes an optional value that we construct explicitly and a broken piece of code that doesn't run, that uses the printline macro to either print the value or print that the value contains nothing. Then we have a second segment of the code that is separate from the first, where we build up a vector of options that contain i8. We instantiate this vector with the numbers from 1 to 10 using the sum constructor, using sum and the number. At the bottom, we have another bit of broken code. Let's look back at the first one. The intent of this code is to print a value out if a value exists. Otherwise, print that the optional value doesn't contain anything. For this purpose, we could match on the optional value, but in this case, we'll use iflet. Using iflet allows us to match on some value that the optional value contains. If it succeeds, we'll print the value, having been destructured. And if it doesn't, we'll print that the optional value doesn't contain anything. This is a more concise way to write the match and allows us to not be exhaustive in our match. In the second batch of broken code, we have an optional values vector that we are popping values off of. Now, if we call pop once, it'll only pop 1 value off, but we have 10 values in the vector. For this purpose, we can use while let and do the same destructuring. While let allows us to iterate through this vector until it returns a none value and destructure the value out of the optional value. Note that when popping, we get an optional value back, and then the actual value in the vector can also be an optional value. So we have 2 optional values stacked on top of each other right now. While let allows us to stack some destructurings to the point at which we can get at the value. In result 1, we have a new struct that contains a value of U64. We also derive partial equality and debug for both the struct and the error enum that we use in our result type for the implementation of the new method inside of our struct. You can see that currently our implementation always returns OK with the positive non-zero integer constructor and the value. If we look at our tests, we can see that we have a failure, specifically on the assert equal, where we pass in a negative number and we expect the value to come back as a creation error. that the value is negative. In the implementation of new, we can check to see if this is a negative integer. Remember, we need to return a result type, so we'll wrap this in error, and we'll specify that it's a creation error negative. Then we can also check if the value is 0, and do the same thing. In this case, we'll be using the error creation error 0. Otherwise, we can return OK with the value. In Clippy 1, we see the first set of Rust code that will trigger the clippy linter. The clippy tool is a collection of lints in addition to what the Rust compiler already tells us. In this case, we can see that the Rust compiler, with the clippy lints added, is warning us about a strict comparison of float32 or float64. The help message here tells us that we should consider comparing them with some kind of error. To learn more about this particular error, you can click on this link in the help text. What this means for us is that when we compare these two floating point numbers, we want to do it within an error boundary. So because two floating point numbers can have very small differences when we operate on them, doing exact equality means that we could have a difference of 0.0000000000001, which might not matter to us, but will indicate in our program that these two values are not exactly equal. So what we are going to do is define a number, typically called an epsilon, that we care about. In this case, I'm going to start with 0001. And you can see that these numbers are both 1.233, and then they differ at that point. So we're going to say that that number is the number we care about. Instead of doing direct equality, what we're going to do is do x minus y, get the absolute value of that, and then check to see that it's below the error boundary. Note that this passes Clippy's requirements, but we're not quite done yet. If we Rustlings run Clippy 1, we can see that we got a success, so they're effectively the same number. If we cared to be more precise, we could add a 0 to our error and run this program again. Note that the same code that is more precise also satisfies Clippy, but now these two numbers are not considered equal because we care about a higher precision than we did before. In Clippy 2, we have a mutable variable called res equal to 42, an optional variable that is sum12, and a for loop over an optional value to add x to res, and then we print line macro the result. Clippy tells us that we have a for loop over an optional type. This is more readably written as an if-let statement. So let's rewrite it as an if-let statement. Using if-let, we can destructure x from the sum in the option, and if it exists, add it to res. Arc1 presents us with a couple of use statements that include threads and something called arc. Arc represents a thread-safe reference counting pointer, and arc stands for atomically reference counted. You may know of this idea from old iOS Objective-C code or something like that. What arc does is provides shared ownership of a value allocated in the heap. Invoking clone on arc gives you a new arc instance, which points to the same allocation on the heap as the original source arc. What arc will do is then increase a reference count, and it will not drop the value inside of the arc until the last reference is dropped. In this code, what we need to do is set a value for shared numbers, and then also create an initial binding for child numbers, such that we can use the value inside of the multiple threads that are spawned for the range 0 to 8. Note that numbers here is a vec, which we've told the Rust compiler to infer the type of with this underscore, and also told it the type by using a range of 0 to 100 as U32. For shared numbers, what we'll do is create a new arc. Note that we also need to use a new binding for child numbers. We have a number of places we could put it, including right below shared numbers or inside of this loop. We're going to do this inside of the loop so that we create a new clone and increase the arc reference counter for every offset that we spawn a new thread for. Note that shared numbers is a new arc that contains the vec. For each offset in the range 0 to 8, which we spawn a thread for, child numbers clones shared numbers, which increments the arc counter and allows child numbers to access the same data. In iterators 2, we have a couple of things to do. The first one is that we need to complete the capitalized first function. This will pass the first two tests, which capitalize hello and deal with empty strings. Then we'll have to finish these two to-dos in test 3 and test 4. Because we can't really progress through the Rust errors without filling in this additional code, we'll comment out test 3 and test 4 so we can work on test 1 and test 2. Our first issue is that there's no method named collect for type car in the current scope, specifically at first.collect. This is because first is a character, which we split out using cars here, and get using the next function. We can turn this into a string so that we can concatenate it with the rest of C by using toString. Note that we aren't currently capitalizing hello in our test. With the first converted to a string, we'll also uppercase that string and then concatenate it to the rest of the string. Let's uncomment test 3. We now need to use iterators to take the words vec and turn it into a vec of strings that are capitalized, in this case, hello and world. We can do this using the .iter function, which returns an iterator. We'll then map over the iterator and capitalize each string using our capitalize first function. Finally, we need to collect the iterator. When we collect the iterator, we need to turn it into a type. In this case, we've specified capitalized words is a vec of strings, so that's what we'll collect into. If we uncomment test 4, we can see that we need to do a very similar thing with words, hello, space, world, where we end up with a string hello world instead of an array hello world. Luckily, the code that we just used in test 3 also works for test 4 if we change the type signature. Note that instead of putting the string type on capitalized words, we can also do what's called a turbofish. This is a turbofish, which allows us to specify the type that we're collecting into of capitalized words as a location that we call collect. In iterators 3, we need to both complete the divide function to get the first 4 tests to pass, and then uncomment the last 2 tests and fill in values for x in the last 2 tests using the division results in those 2 tests. We'll start with the divide function. The divide function is a public function that takes 2 integers and returns a result that is either an integer or a division error. You can see that division error is defined in the same file and is an enum that can either be not divisible with an argument of not divisible error or divide by 0 error. In addition, the comment above the divide function says that we should calculate a divided by b only if a is evenly divisible by b. Otherwise, it should return a suitable error. So first, we can test to see if b is equal to 0. If it is, then we need to return an error of a division error divided by 0. Otherwise, if a is divisible by b with no remainder, we can return the division of a over b. And finally, if neither of those count, we can return a division error. The division error takes a struct that is a non-divisible error with the dividend and the divisor. Now that we've passed the first 4 tests, we'll pass the next 2. We'll uncomment the second to last test and fill in x here. Note that we have numbers, which are a vec of 4 different numbers, and we have division results in which we take numbers, which we put into an iterator, and then map over with our divide function. This leaves us with division results, which is still an iter. So we know we need to collect it. Now, if we look at the assert equal, we can see that we're expecting a result type that wraps the values that were divided. So we want a result that is either a vec of i32s or the error type. We know this is the return value because this is the return value that divide gives us, except for the fact that the i32s are not in a vector when returned from divide. They're in a vector now because we operated over a vector. So divide was applied to each individual number. So the type result, which can either return a vector of i32s that we divided over or a division error. We can do the same thing for the last test using the same code, but this time the return type is different. Here we have a vec of result types. What we need to do here is pull the vec out, and collect will know how to collect this into it, and our tests are passing. In iterators 4, Rustlings wants us to implement factorial. In case you're unaware of what factorial is, factorial, when passed a number, will multiply that number by all of the numbers preceding it down to 1. So if we pass in 1, it multiplies by itself. If we pass in 2, it multiplies by 1. And if we pass in floor, it's 4 times 3 times 2 times 1, which is 24. Now, there are plenty of explanations how to implement a factorial function on the internet in other languages. And this particular exercise wants us to not use the return keyword, imperative style loops, additional variables, and also not recursion. Perhaps obviously, since we're in the iterators exercise, we're going to use an iterator for this. We'll start by using a range to iterate from the number 1 all the way up. Because it doesn't matter what order we do this in, it doesn't matter what order our range is in, because multiplication will work the same across all of them anyway. Note that in this range, we're using an equal sign on the end of the 2 dots, which means that this number is going to be included in our range, whereas normally it would not. Now we can use a fold on top of this range. So we have a range of numbers. We fold over that range. We set our accumulator to 1. We get an accumulator and a value in our anonymous function, and we multiply the 2 together, which results in this entire list getting multiplied 1 by 1 against each item in the list. Now this works, but it's also not the most rusty way to do this. The most rusty way to do this including iterators, is to use product. Now we've used an inclusive range from 1 to our number and called product on it. Product is a trait, and it's a trait to represent types that can be created by multiplying elements of an iterator. By creating a range in our iterator, we can then call product on that range. If we scroll down, there's an implementation of product for U64s, and U64s are the numbers we were given to work with. If we look at the implementation of product in the Rust source code, we can see that product uses fold under the hood with multiplication. This is very similar to what we wrote the first time when we wrote out the fold manually. It's nice to know that these traits exist because they can do various things for us and shorten our code by great amounts. Traits in Rust are how we define behavior that can be shared across types. So in this case, we have an append bar type that declares a function append bar, and we can implement this trait for any type. In this case, our task is to implement append bar for the type string. We're going to use the same function signature as in the trait. And then since we're implementing for type string, self is a string. We can also use push string to push a string slice into self, and we'll need to return self at the end because push string doesn't return self. Note that because we haven't borrowed as mutable, we can't use push string yet. So we have to declare ourselves as mutable so that we can push bar on. And that's how you would implement a trait which defines a function as shared behavior for a specific concrete type. In traits 1, we said that we could implement a trait for any type. In traits 2, our task is to implement the trait append bar for a vector of strings. If we look at the tests, we can see that a vector with one value, foo, that has bar appended to it results in bar and then foo being popped off the stack. If we look at our test, we can see that we have a mutable foo that is a vector that starts out as just a vector of foo and then receives a bar. If we pop an element off of foo and unwrap it, we get the string bar. If we pop the remaining element off and unwrap it, we get a string foo. So the implementation for append bar is going to push bar into the vector. We'll specify that we're implementing append bar for a vector of strings. We'll use the same function signature as specified in the trait. So now we have an implementation append bar for vector of strings. We have the function append bar where self is a vector of strings, and we can push a string onto that vector and return the vector. Note that we also have a mutable self. This passes our tests. Generics in Rust give us a way to specify that the thing that we're building can operate on multiple different types. Usually generics are used in place of type signatures or struct signatures. In this case, vectors are implemented on a generic type. So in this case, when we create a new vector, we can tell it what concrete type we want it to use, and it will use that. This is us using a data structure vec that has been implemented on a generic type. In generics 2, we have a concrete struct wrapper that works on a concrete type U32, and we have implemented wrapper for U32. Other than that, we have a couple tests that use this struct and the implementation. We have to rewrite it using generics so that it supports wrapping any type. Note that in the first test, we're using integers, and in the second test, we're using strings. To convert this to operating on a generic type, we need to replace the concrete type U32 with the generic type T. T doesn't mean anything. It's just a letter. We can say that the wrapper struct operates on a type T, where the value is a T. The implementation on T for wrapper allows us to pass a value of type T into new and set the value on the struct. This has allowed us to pass the first test. Our second test is still failing because we have an assert that we no longer need. If we enable the second test, we can see that our wrapper type now operates on integers and on strings using the same APIs, just like the vector type that we used in generics 1, as well as a number of other exercises. In generics 3, we have a struct report card that we need to change one of the fields on to be able to accept a generic type. In this case, it needs to accept F32 as well as strings. For this, we'll specify a generic type T for the grade type. Note that if we just put it on the grade type, T can't be found in scope because T isn't anything. It doesn't identify anything. T is not special. It's just a character that we chose to use. So we also need to say that the thing that we're referring to is a type. So now that we've specified our struct type is parameterized over type T and that we use type T as the grade, we can take a look at the implementation, which expects a type argument now and doesn't currently use one. If we just put the T on the right-hand side of the report card, we can see that it's not found in scope. So we need it after the implementation as well. Now with the generic type in place, the program is trying to use the generic type and trying to use the report card specifically, but T cannot be formatted with the default formatter. That is, it can't be put into a format macro like we are right here. To fix this, we're going to say that T has the display trait. The display trait is implemented for any type that can be used in format. Note that now that we've said our generic type T has to implement the display trait, our tests are mostly working. If we go down to the tests, we can see that one of them is actually wrong. In this case, we're trying to assert equal that reportCard.print achieves a grade of A+, but we're not passing in A+ here. So let's do that. And now we can see that the grade that we used in the first test, 2.1, and the grade that we used in the second test, A+, both work. And that's how we use generics to constrain them to a specific trait and work across multiple types.